Hello, good morning all. Today we are going to continue with our series on wave mechanics. And yesterday we were revisiting some of the concepts that we had already covered previously also, but just for the sake of revising, we were doing it. Today also, I'm going to start with the same revision sort of thing, and then we'll do few questions that have come in previous year exam also, so that you get an idea of how things are being asked in exams. Okay, so without wasting time, let us start. Okay, so let us start with one of the most used wave packet, or you can say wave function, that is the Gaussian wave function. So, let us start with this wave function. Psi x is given to be equals to a e की power of minus a mx square upon h cat, and then you have this plus iota t. And here capital A and small a are positive real constants. Are positive real constants. We want to find first normalization constant. We want to find the normalization constant. So in order to find the normalization constant, I have already told you I have to do this particular integration equated to 1. And this is equals to minus infinity to plus infinity psi star psi dx. And which is equals to minus infinity to plus infinity. You will get, I think, a modulus square minus of 2am x square upon h cat, and then you have dx. And from here, you know that this particular entity should be equals to 1 because this is probability of finding the particle anywhere in the space. And from here, you will get a mod whole square. You just from e keep exponential of minus of 2am x square upon h cat dx. And this is a well-known integral. And from here, you know, this will be equals to 1 a mod whole square 2 times integration from 0 to infinity e की power of minus of 2am x square upon h cat, and then this is dx. And this all equals to 1. From here, one can identify that this is equals to 1 upon 2 root over pi upon this particular coefficient. This is 2am upon h cat, and this entire thing equals to 1. So this gets cancelled. So your modulus of a turns out to be, I should write 4. This is power 4 2am upon pi h cat. So this is your normalization constant. Okay. Having found normalization constant, we want to figure out for what potential energy, for what potential energy, for what potential energy Vx does psi satisfy the Schrodinger equation. Okay, so we want to find what is that potential for which we are going to get, we are going to see that this psi satisfy this particular Schrodinger equation. So our psi, as you are aware, is this psi of x is equals to I think A we have already found, so I'll write modulus of A is equal to root over, sorry, not root over, power 4, 1 by 4, sorry, 2am upon pi h cat. This is something that we already know. And I know that my psi of x is equal to minus of, I should write from so minus of, sorry, a m x square upon h cat, and then plus, sorry, minus iota at. So this is what is my, you can say, no, this is not h cat square, this is h cat. Okay, this is my wave function. We want to find that this wave function would be applicable for which potential energy. See, this is a wave function. This will satisfy the Schrodinger time-dependent Schrodinger equation given by iota h cat del psi upon del t is equal to minus h cat square upon twice m, and then you'll get del square upon del x square psi plus b as a function of x psi. Now here, if you just replace this particular thing, so I'll do it step by step. So what I'll do, first I'm going to find this particular fellow on the left hand side. So on the left hand side, this is iota h cat del by del t of a e की power. So I'm writing a, if necessary, I'll replace this, don't worry. H cat minus iota at. So what I'm going to get, I'm going to get minus iota a. I mean, this is, I have not multiplied iota h cat. So iota h cat minus iota a would come, and then entire this thing, a exponential of minus of a m x square upon h cat, and then minus of iota at. And so definitely I can write that my iota h cat del by del t of psi is simply minus of iota a into iota h times psi, which is equivalent to writing h cat a psi. So this is my equation number 1 on the left hand side. On the right hand side, we have two terms. So let us first evaluate this term. So if I differentiate it once, what I'll get, and then I'll multiply with minus h cat square upon twice, and don't worry. So the derivative would be with respect to x if I want to do. So with respect to x, if I do, this will be like a minus of 2 am x upon h cat, and then you have this entire psi, right? Okay, I can absorb this a inside psi. Okay, so this will be minus 2 am x upon h cat. If I want to find the second derivative would be minus of 2 am upon h cat and then psi, and then minus of 2 am x upon h cat, and then you have del psi upon del x, which I'm going to write directly 2 am x psi upon h cat. So overall, I will get this thing. This is del square psi upon del x square, which is equivalent to 2 am upon h cat. Take a negative component. This would be 1 minus of this x square will remain there. So I'll write this 2am also will remain there. So this will be minus of 2 am x square upon h cat. And then I'll take a psi form. So I'll take a psi. So overall, I know that on the left hand side, I have h cat a psi. On the right hand side, I have minus h cat square upon twice. So I'll write simply h cat square upon twice. Negative, negative cancel. So this is, and then you have this 1 minus of 2 am x square upon h cat, and then again you have this psi, and then again bc. So overall, I'll take this common out, and what I'll get h cat a, this and this, not this, sorry, not this. So this will get cancelled. 2m would get cancelled. So you have a h cat here as well. 1 minus of 2 am x square h cat plus v. So this a h cat and a h cat would get cancelled. So your v as a function of x will, okay, this h cat will survive now. This h cat would survive anyway. And this AH would come inside also. So I'll write here, not this way. I'll write AH cat inside, and here I'll write A square and then H cat. So H cat cancel. So your V as a function of X would be a quadratic function. This would be 2m A square and X square. So V as a function of X would be simply 2am A square X square. Okay, so for this potential function, you'll get this kind of wave function. Psi as a function of X would be this. That is a e to the power minus am x square upon h cat minus iota at, where a is given by 2am upon pi h cat raised power 1 by 4. Now, yesterday I taught you one thing, that if your wave function, okay, so one more thing, yesterday we were studying that were finding expectation values. So let us try to evaluate the expectation values. And then we'll try to see the validity of, we'll try to also establish the validity of Heisenberg principle here. So I have not taught you right now Heisenberg principle. I've just given you an idea as to how to work with Heisenberg principle. As we go along, we are going to see all these things in greater detail. So expectation value. So I want to find the expectation value of X. I'm giving you a minute, try to find this. So I hope this is quite easy for you. See, if I want to find the expectation value of X, this will be minus infinite to plus infinite X psi mod whole square dx. We understand that this particular function would be simply e to the power of minus of 2am x square upon h cat. There would be some constants, I'm not denying that. But overall, this particular function is an even function. And this psi is an odd function. So overall, this integrand would be an odd function. Since this integrand is an odd function overall, so from minus infinite to plus infinite, this integral, that is x into mod of x into mod of psi whole square would be equal to 0. So clearly the expectation value of x would be simply 0. Now, if we want to evaluate a few more things, and those are these. So we want to evaluate the expectation value of x square. So expectation value of x square, I think you would need an integral. So I'll supply you an integral at first and then try to do this. So I'm giving you an integral so that you are able to do this. So from 0 to infinity, if you want to evaluate x square into exponential of minus of ax square, then this integral turns out to be root over pi upon 4 and then 1 upon a raised to power 3 beta. So this is the integral that I'm already supplying you. Probably it may be used here. So this integral I'm supplying you. Now try to find expectation value of x squared. So now if I want to find the expectation value of x square, how will I do? I will try to find this integration minus infinite to plus infinite x square, and then I'll get psi mod whole square dx, which is equivalent to writing minus infinite to plus infinite x square into mod of a whole square, and then you have this exponential of minus of 2am x square upon h cat, and then you have this dx. You want to find this, and I already know that this would be equals to what? This mod a whole square would be simply equals to, I've already figured it out somewhere. This will be equals to 2am upon pi h get raised to power 1 by 4, and then this square. So I'll get 1 by 2 here. So minus infinite to plus infinite. This is x square. In fact, I'll do it from 0 to infinity. So I'll take a 2 outside. And then you have this exponential of minus of 2am upon h get. And then you have this x square here. And then I want to integrate this. What I'll get? I will simply get this as 2am upon pi h get raised to power 1 upon 2 into just use this particular formula, which is equals to root over pi upon 4, 1 upon a raised to power. So instead of a, you have 2am, and then you have this h cat here raised to power 3 by 2. Okay, so I think this will be equals to what? So I'm writing the expectation value of x square, which is equivalent to writing, I guess this will be root pi is here and root pi is here, so this gets cancelled. Forget about this. I think there is a 2 root 2 here. There is a 2 root 2 because 2 raised to power 3 by 2 is 2 root 2. So this gets cancelled. So 1 over 4 remains. Okay. This root over m is there, and this m is raised to power 3 by 2. So 1m survives below. This a is raised to power 1 by 2. This a is raised to power 3 by 2. So 1 a also survives. This is h raised to power 1 by 2. This is h raised to power 3 by 2. So h cat survives. So overall, I can write that x square, the expectation value of x square would be h cat upon 4am. Okay. Now, if one wants to find the measure of the uncertainty in position measurements, so that would be delta x, and that is simply the standard deviation, and which is equivalent to writing root over x square minus x, like expectation value of x whole square. I know this is 0, and this would be equals to what? This would be equals to root over h cat upon 4a. Okay. Now, if I want to find the expectation value of p, yesterday itself I told you that if I want to find the expectation value of p, this will be equals to minus infinite to plus infinite, and then you have the psi star, and then again psi. So and you have minus iota h with psi star, and you have del by del x of psi. Just remember one thing. From here, you have this time-dependent factor e to power minus iota at, and here you have e to power iota at. In psi star, you will have this. So this time-dependent factor would get cancelled. So you don't have any imaginary term here. So clearly, this integral would be real. Understand that the expectation value of momentum or anything should be a real thing. So overall, this entity would be 0 because there is minus iota h get in front. So if this integral survives, then the expectation value will come as complex, and that does not go in line with the physical understanding of expectation value. After all, expectation values are the average values, so they cannot be complex. Okay, so this is point number 1. If you want to find, you can find it on your own also. But yesterday also I exclaimed on the same. I told you, explained the same thing. So I hope you are remembering this. So this expectation value of p, you can place it as 0, and you can find the expectation value of p square. So expectation value of p square would be simply equivalent to writing minus infinite to plus infinite, and psi star would be writing. I should write a mod whole square at first, and then I'll write psi star. So psi star will give you exponential minus. Okay, and plus iota 80. And then you have this second derivative of um, second derivative written here. So I should not write this way. I should write in terms of psi only. So it will help me, I think. So because this is something that we have already figured out from somewhere. So we already know this the double derivative we have written somewhere. So your double derivative is this. It is equals to minus 2am upon h cat 1 minus of 2am x square h cat times psi. So I'm going to directly use it so that it does not disturb. So what I'll do, I'll simply write this p square is equals to writing minus infinite to plus infinite psi star, and I already know this is equals to minus of 2am upon h cat 1 minus of 2am x square upon h cat and then psi and then dx. Okay, and if I take this common out, this 2am upon h cat, if I take this common out, I think there is some okay. So I know that my p square would be equals to what? My p square would be equals to uh, h cat whole square and then del square upon del x square. So I missed one negative here. Minus h cat square I have to write. So I'll write minus h cat square here. So I've written minus h cat square. I'll absorb this up. So this will remain. This will become, I think, 2a m h cat here, because this gets cancelled and this negative gets absorbed here. And from minus infinite to plus infinite, minus 2a m x square upon h cat. And then you have the psi star psi, which is equals to mod a whole square. Uh, or I should write once psi mod whole square so that things remain easy for you. Okay, so this is one thing. Okay, and I understand that if I integrate this minus infinite to plus minus, and I don't want to use that expression of psi because after all, you understand one thing, that if I want to write the first term in this integral, this will be equals to minus infinite to plus infinite psi mod whole square dx. And then the second term would be equivalent to writing minus infinite to plus infinite 2am upon h cat. And then you have this x square mod of psi whole square, this integration, which this is equals to what? This is equals to simply writing expectation value of x square. And there is some constant indeed. So I'll take that out. So overall, and this is equal to writing what? This is equal to writing the total probability of finding the particle, which certainly would be unity. So I'll write this as 2am h cat, and then I will write, I think, 1 here, and then minus of 2am upon h cat times the expectation value of x squared. And what is the expectation value of x squared? Just think about that. We have already figured it out. So expectation value of x square is equals to, I think this was equals to h cat upon 4am. You can you can see that we've already found it. So basically, this p square, the expectation value of p square will come out as am h cat. And if you want to find the uncertainty in finding the uncertainty in the position measurement, that would be delta px, and that is simply equals to sigma p, and that is equals to root over am h cat, because expectation value of p is 0, so its square would be 0. And if you want to evaluate what would be the product, this sigma x into sigma p, it will be equals to, I think, root over am h cat times what was sigma x? Sigma x was h cat upon 4am. So h cat upon 4am root over. So that would be h cat upon 4am root over, and this will give you h cat upon 2. So basically, we are validating the, basically what happens is that sigma x into sigma y, according to the Schrodinger's expression, is always greater than equal to h cat by 2. We've managed to somehow get an equality here. So we'll say that that Heisenberg principle of uncertainty holds here. So, okay, here we are achieving an equality. So this particular product will come out as h ket by 2. Okay, so such questions are mostly asked in your examination. Now, we've already done a few more things in our lectures. So let us try to revise those things also. So we were actually doing something called as time independent. Time independent Schrodinger equation. So we were doing time independent Schrodinger equation. And in that, we actually wanted to find psi as a function of x. And we actually used something called as the method of separation of variables. So just to revise that entire thing. So basically, what was the motivation? So, so motivation here was that if we are solving this iota h ket upon del by del t times psi is equals to minus of h ket square upon twice in del square upon del x square psi plus vx psi. So we are going to use mostly the function which are the potential functions which are independent of t. So in this course, we are going to use v, which are only functions of x and not dependent upon time. So these are not dependent upon time. So so naturally, one of the most important questions that arises is how to get this psi. Because this is a non-linear, so this is a linear partial differential equation, and we want to find what? We want to find what would be this psi, right? And one of the ways to achieve this is to use something called as method of separation of variables. And once we use this thing, what do we get? So I'll write this as capital psi here. Okay, and this is small psi. So what we'll get that minus h ket square upon twice in del square upon del x square plus vx psi is equal to e psi, and this e is a constant here. This e is a constant here, and this phi as a function of t is a time dependent term, which we get equivalent to some constant you can place if you want to e to the power minus iota et upon h ket here. Okay, so this is how you obtain the solution as. So this equation is called as the time independent Schrodinger equation. This equation is called as the time independent Schrodinger equation. Okay. Okay. So this is an important zone where you will find that a lot amount of questions are asked, and let us try to revise this using questions. So let us revise it using some questions. Okay. So one more thing that one needs to see, that this particular equation can also be written in form of operator. So basically, what I can write minus hk square upon twice m del square upon del x square. This I can write it as a kinetic energy operator plus v times psi is equal to E psi. So basically what it is equivalent to, it is equivalent to writing that hk is getting operated on psi and it gives me E psi. So it turns out to be a eigenvalue problem. And these psi can be written as eigenfunctions. This wave function is an eigenfunction for this particular eigenvalue problem. Now, let us try to do a few questions on this particular concept. Okay, so a particle of mass m is subjected to the potential energy Vx is equals to half of kx square. At a particular time, it has the wave function. It has the wave function psi of x equals to a e raised to power of x e raised to power of minus of x square upon a square. Okay. If the particle has a definite energy, so basically what happens here in this time independent Schrodinger equation, this E is a constant here. So this is a definite energy here. So if the particle has a definite energy, then we want to find the value of A. Then find the value of A. Okay. So how to go about this particular problem? See, understand, if somebody says that this has a definite energy, it implies that energy is a constant. So I can use, and see here, this wave function is completely dependent on x. So I can use that h ket psi is equal to E psi. So this is my, using this time independent Schrodinger equation, I can solve this equation. I can solve this question. So this is my time independent Schrodinger equation. Okay. And see, I know this is equals to writing minus h ket square upon pi m. Let us first find del square psi upon del x square, which will be equivalent to, and if I want to find A, I'll use it. I can find this A also. But if I find that there is a need, I'll do it. If I don't find there's a need, I'll not do it. Okay. So we'll see this. Let us first find how this particular thing would be. As first, let us find the first derivative. The first derivative would be simply A e raised to power of minus of x square upon a square plus a x minus 2x upon a square e raised to power of minus of x square upon a square. And again, if I want to differentiate it, so this will be equivalent to writing minus of h ket square upon y m. The derivative will be equals to minus of 2x, and this I want to place this a outside so that this does not disturb me time and again. So this will be minus of 2x upon a square e raised to power minus of x square upon a square plus again this will be equals to sorry minus 2 sorry this would be I think I should write it in. Okay. So this will be equivalent to writing minus of 4x upon a square e raised to power minus of x square upon a square and then plus this again minus 2x upon a square. So this minus 2x upon a square you will get. So this will be 8x cubed upon 8 upon a raised to power 4 e raised to power minus of x square upon a square. Okay, so I think there is no mistake till now. If there's a mistake, kindly see this, verify this. Take this x common out and e raised to power minus x square upon a square also common out. So you'll get minus of h ket square upon twice n x and e raised to power minus of x square upon a square. If you take common out, you'll get minus of 2 upon a square. I think this is, I think 6. So I should write minus 6 upon a square plus 8. I've taken x common out, so I'll get x square here upon a raised to power 4. And this will be simply psi. Okay, so this is h ket psi. And this should be equivalent to E psi. Okay, I forgot to write. This is minus h ket square upon, no, this is not h ket psi. So h ket psi, this is, I think, k psi. I should write. This is kinetic energy operator. Now, I want, this is not equal to E psi, sorry. I will have to use one, v as a function of x, right? So, h ket is equals to what? It is equals to minus h ket square upon twice m. And then I think this is minus 6 upon a raised to power 2 plus 8x square upon a raised to power 4 sine plus v. V was what? Half kx square. So half kx square sine is equals to E psi. Okay. Now understand that this particular thing E is a definite thing, that it is a constant thing. So we want to get we want to remove the terms which will depend upon x anyway. So the terms that depend upon x are these and this. See, we want to remove them. Okay, so the side, remove this throughout. So you'll get minus h ket square upon twice m times 8x square upon a raised to power 4 plus half kx square. This should be equal to 0, which implies what? Which implies that k upon 2 should be equals to h ket square upon 2m a raised to power 4 into 8. So this 2 gets cancelled. And we want to find the value of a. So the value of a would be simply, there's some mistakes in there. I think there's some mistakes somewhere. We have to see that if there is a mistake. Let us try to find mistake. So minus h ket square upon twice n. This is del by del x of e minus of x square upon a square plus I think this is a into minus 2x square upon a square e raised to power minus of x square upon a square. Okay. So this is d by dx, and I want to differentiate this. This would be simply minus 2x upon a square e raised to power minus x square upon a square. Again, you see this. This is minus 4x upon a square. This is fine. And if I again try to do this, the derivative, This is what? This is, sorry. So if I again do the derivative, this will be 4, I think, not 8. This would be 4. Okay, this would be 4 here. This would be 4 here. This would be 4 here, sorry. And, this would be 4 here. So overall, this is 4 throughout, and this would be 4 here. Okay, so a raised to power 4 would be equals to hk square, 4 times hk square, sorry, divided by mk. And what would be a? A would be simply 4 hk square upon mk, all raised to power 1 by 4. So this is the value of a. Okay, so the concept involved was the constancy of E in case of time-independent Schrodinger equation. Now let us try to do a question from TIFR 2015. Okay, and this is a good question, I think. The question says that a particle is moving under one dimension in one dimensional under one dimensional potential Vx such that for large positive values of x, such that for large positive values of x, Vx is equivalent to kx raised to power beta, where k is a positive constant and beta is greater than or equal to 1. If the wave function has the form exponential minus x raised to power lambda, then which of the following is true? So option number 1 is lambda is equals to beta upon 2 plus 1. Option number B that was given in the exam was lambda is equals to beta. Option number C given in the exam was lambda is equals to 2 beta minus of 2. And option number D that was given in the exam was lambda is equals to beta square upon 2. So how to do this question? See, understand the potential is given to be Vx. Okay, the wave function is completely dependent upon x. So we'll use the time independent Schrodinger equation. We'll use the time independent Schrodinger equation. So this is given to be equivalent. So basically we can multiply some a also and do the analysis, but I'll assume that a is not required. And because on the both sides we can cancel that a, so I'll use this particular thing only, exponential minus x raised to power lambda. Okay. Okay. So let us first write the equation, which is minus hk square upon twice n del square upon del x square psi plus vx psi is equal to e psi. Okay. Now just let us first find this. So let us first find del by del x of exponential minus x raised to power lambda. It will be equals to minus of lambda x raised to power of lambda minus 1 exponential of minus of x raised to power lambda. Okay, and if I do the second derivative, I can write this particular thing as psi. So basically it is equals to minus lambda x raised to power lambda minus 1, and this is psi. Okay, if I want to find the second derivative with respect to x would be the derivative here. So minus lambda minus 1 x raised to power of lambda minus 2 exponential minus x raised to power lambda Okay, I should have used this. Okay, fine. I've not used it. So, and the second time we'll get plus lambda square x raised to power 2 lambda minus 2 exponential of minus of x raised to power. Okay, so I know that this is my the second derivative of the wave function exponential minus x raised to power lambda. So minus hk square upon twice m del square upon del x square exponential of minus x raised to power lambda is simply equals to minus lambda minus 1 x raised to power lambda minus of 2 plus lambda square x raised to power 2 lambda minus 2, and this I think if I take common out, okay, and further I can take this particular thing common out also, so I'll take this common out also. So x raised to power uh, let me take x raised to power 2 lambda minus 2 common out, so I'll get simply, and I think there would be some minus hk square upon twice as well, sorry. So here you will get minus of hk square upon twice m. I've taken this common out, and from here you know this equals to lambda square minus of lambda into lambda minus 1 divided by x raised to power, I think, lambda. Okay, and then there would be some exponential thing would be written there. So exponential of minus of x raised to power lambda. So this is one thing. So this is hk square, sorry, hk psi. And if I want to use my Schrodinger equation, this is equivalent writing minus hk square x raised to power 2 lambda minus 2 divided by twice m lambda square minus lambda into lambda minus 1 divided by x raised to power lambda e raised to power plus vx psi is equals to e psi. So I'll forget about this because this is non-zero. Now you see, there is a trick that I will use so that things become easy. I'll try to use this. So see, one thing usually one can use, that energy should be constant. Energy should be constant. This is one thing that one can use. Uh, Another thing that I think that it can be helpful in that particular evaluation is that just try to take this through common. So I'll divide this up. So this will be minus hk square upon twice m lambda square minus lambda into lambda minus 1 upon x raised to power lambda plus. Now understand that for I'll write for large values of x, for sufficiently large values, I can write my Vx is equals to kx raised to power beta, and then I will have this division of x raised to power 2. So I'll get my minus 2 lambda plus 2 is equals to e exponential 2 minus 2 lambda. And this is a constant, mind you. Now for large values, if this is the case, so for large value, if I take x tending to infinity, my right hand side becomes 0, provided 2 minus 2 lambda is negative. Okay, provided that 2 minus 2 lambda is negative. If my 2 minus 2 lambda, that is lambda, is greater than 1, then my left hand side becomes, we'll take another case also. So if 2 minus 2 lambda is negative, then my left hand side becomes 0. So this becomes 0. Oh, not right. Sorry, right hand side. No, sorry. So if 2 minus 2 lambda is negative, then the right hand side becomes 0, right? So for that, my lambda should be greater than 1. This is point number 1. Second, just figure out from here that as x tends to infinity, if lambda is greater than 1, this particular fellow would go to 0. Okay. And what is required? This is required that it may so happen that this k, because nothing is given quite explicit in the question, so one can think that this k can be equals to hk square lambda square upon twice n. This is absolutely fine. One can think that this k can be always written in some this form. Okay, this form. That is, it can be written as constant. So understand that this particular fellow should go to zero. That exponent to this should go to zero. Exponent this should go to zero. Otherwise, there would be some x dependent term, and this would go to zero only if beta is equals to 2 lambda minus of 2, which implies beta should be equals to, sorry, which implies the lambda should be equals to beta by 2 plus 1. And clearly this assimilates this condition, because already we've been given that beta is greater than equal to 1. If beta is greater than equal to 1, then beta plus 2 plus 1, beta by 2 plus 1 certainly would be greater than 3 by 2. So this particular equation is implicit in this. Okay. And what if that another case can arise, that what if lambda is equals to, this case number 2, what if another condition that on k can be that k should be equals to hk square lambda square upon twice. K should be equals to hk square lambda square upon twice. Why? Because if this is not the case, then the entire thing cannot remain zero. So both left hand side and right hand side should be zero. So if 2 minus 2 lambda is less than 0, if 2 minus 2 lambda is less than 0, which implies that lambda should be greater than 1. For this, understand that there should be no x dependent term on the left hand side, because if there is an x dependent term, then there would be an issue, because here you have 0, this will somehow turn up, this will be 0, and if this exponent becomes 0, this exponent becomes 0, then this is x raised to power 0, this would be 1, and if k is equals to minus hk square lambda square upon twice, and then both of side will be fine. So your k should be equals to hk square lambda square upon twice. And in this particular scenario, the lambda should be equals to beta by 2 plus 1, because if this is 0. Okay. Now, case 2 may arise that one may think that, okay, what if that, what if lambda is less than 1? So if lambda is less than 1, then things won't work. Why it won't work? Because then with certainty, both sides are tending to infinity. So you cannot say anything about this, because if lambda is less than 1, if lambda is less than 1, this quantity will go towards infinity, right? If lambda is less than 1, this particular quantity will go to infinity. Here also you see, if lambda is less than 1, and in particular if it is negative, so it will go towards infinity. And here also the same conclusions can be drawn. Okay, the same conclusions can be drawn. So basically, you will not be able to identify the relationship between beta and lambda. So in order that this particular thing, both of the sides agree to the same thing, uh, lambda should be greater than 1. Okay. Another way you can think of is probably, one can think is that, okay, the case number 2, what I was thinking was, one can think that this is 0, that is 2 minus 2 lambda is 0. If this is 0, then lambda should be strictly equal to 1. Then lambda should be strictly equal to 1. And in that particular case, E is a constant. So again, this also implies that there should be Vx must not have an x dependent, because if there is an x dependent term, this will somehow go to 0 only, because as x tends to infinity, this will go to 0, right? As x tends to infinity, this will go to 0. If x is lambda is equal to 1, this goes to 0. There is a constant here. So understand that there should not be an x dependent term. So that implies beta should be equals to what? 2 lambda minus 1. Or in other words, lambda should be equals to beta by 2 plus 1. Here also you'll get the same result. Here also you'll get the same result. But now here is a discrepancy. Here is a discrepancy. Why? Because beta is already given greater than equal to 1. If beta is greater than equal to 1, then lambda strictly would be greater than equal to 3 by 2. So this cannot be the case. Lambda cannot be equals to plus 1. Lambda cannot be equals to plus 1. So there is a discrepancy. So overall, I believe the answer would be that in order that this, and you see, if you take lambda less than 1, if you take lambda less than 1, then certainly you will find that you will not be able to write any relationship between beta and lambda. So the most appropriate option in the exam would be lambda should be greater than 1, precisely. Lambda can be written, lambda should be greater than 1, and precisely lambda can be written as beta by 2 plus 1. Certainly this assimilates this case because beta is already greater than or equal to 1. So lambda would be greater than or equal to 3 by 2. So this assimilates this condition. And additionally, you can also think that k should be written as hk square lambda square upon twice n. Why I cannot say this with certainty? Because see, I have not normalized the wave function and things like that. And nothing of that sort has been given to me. So it has been a question which invoked a sort of an intuitive response that what do you think? So I think the answer would be lambda is equal to beta by 2 plus 1. So I think option number 1 suggests me the same thing. So here it is. Okay, so this particular question was asked in TFR 2015. Okay, tomorrow also we are going to start with time independent equation. A few of the concepts that we've already done, we'll see tomorrow as well, like probability density and things like that. And after having a solid revision, we'll start with an important topic of quantum mechanics, which is called as one-dimensional potentials. So I hope to meet you tomorrow. Till then, take care. Bye-bye.